that these earthquakes are giving off neutrons. So within about 2 weeks, because it's only 2 weeks after that, we had formulated a reason for why that might happen. And that has to do with resonances. On the left-hand side of this picture, you see resonances where electrons and positive charges in atoms and molecules create a plasma frequency. On the right-hand side is if you have a liquid drop model of a nucleus, then when the protons go back and forth opposite the neutrons, you get what's called the giant dipole resonance. Giant dipole resonance physics is not new physics. It's been studied for years. If I have a damped harmonic oscillator, I can get the total cross-section that a gamma hits a nucleus and gives you an excited nucleus. Once it's hit by a gamma of sufficient energy, maybe 15 MeV, then the nucleus goes into an excited state, and then it can fission. Even if it would not naturally fission, it can be caused by gamma rays. Those are the Feynman diagrams for it. We take iron as an example. If you start with iron 56, one of the most stable nuclei around, you can hit it with a photon and excite it, or you can get that photon, then called virtual, from a scattering electron, and then excite it. So we've been calculating these two different processes frantically because we know, or have a very strong feeling, that this kind of low-energy nuclear physics of induced fission is going to very shortly become very important. And so we're racing to make sure we can get out as many results as we can before the hordes come. Okay? Now, this is what the giant dipole resonance looks like. It looks like a resonance. This is how they do the measurements of that resonant cross-section. You beam dump electrons and you get bremsstrahlung. You focus the bremsstrahlung on a crystal and you diffract it. Each diffraction gives you a different energy. And so if I put a bunch of absorbers at different angles to where you bounce the photon off, then I can plot that versus energy. And that's the way you get curves that look like that. And they do look like that. Now the thing about the Carpentieri events is, aside from seeing neutron production, which I was used to, and we've been claiming that for 5 years or so, he got some weird ones. He got iron going into 2 aluminum plus 2 neutrons, and those 2 neutrons would be fast, maybe 8 MeV, whereas the neutrons we had been predicting, and some people have been observing, are more like thermal neutrons. That's a factor of 10 to the 6th in energy down. Also, he was finding iron going to silicon and manganese with 4 neutrons. And at first glance, you say it looks impossible, which is what I told him, and I'm pretty sure Yogi told him, that it's impossible. On the other hand, he's seen it in batteries. He has seen it in crunching rocks. He's seen it in cavitation. So at some point, as a theorist, I have to say I give up. Okay? It's happening. I just don't know why. Okay.
Excuse me, how big is the Coulomb barrier there? When
None. Zero. Zero.
How can you say that?
Because the electron producing the photon is attracted to the nucleus. It's not repelled. It's not repelled. The electron, all the processes we're using are electrons scattering off nuclei. There's no barrier because they're repelled. By the time the electron excites the thing, there's no barrier because when it fissions, it's going to the lower energy regime. So there are no barriers in this problem. Unlike fusion, where there's a barrier.
You know, this is the first time that I heard about the possibility of fissioning iron or some
Yes,
intermediate nuclear.
Oh, no. Actually, look up giant dipole resonance.
Yeah, but dipole is another thing. So you have excitation of the nucleus and emission of neutrons. But this is a fission. It's something different.
No. If you look it up, I'm sorry about this.
Okay.
This is just basic physics.
If you
Google it,
literature in
Google it, look up the giant dipole resonance, and you will find.
No, se posso dire, c'è un misunderstanding. Il primo processo non c'è una barrier, c'è fotone che viene e mi crea una cosa,
Come è stato eccitato?
excited nucleus. Excited nucleus può decadere con un neutrone, altri neutroni, eccetera, eccetera. Però look at a big heavy nucleus, excited.
I can straighten out the difference. Once you excite the nucleus, you've excited it over the barrier. It doesn't have to go through a barrier. Once the nucleus is excited, you see, fission will have a barrier, but once the nucleus is excited by the photon, it kicks you over the barrier. That's the way giant dipole resonant fission works. So the photon gives you an excited one. There's no more barrier to fission anymore, because now it goes to a lower energy, but you've kicked over the barrier. That's what the photon does. That is not my theory of what the photon is doing. That is the established theory. Okay? We're applying it to crushing rocks. That's not so established.
I'm still curious about
But the established theory of how hitting it with a photon, the photon excites the nucleus over the barrier, and then it just slides down.
Yeah, but you should have a deformation, no? The fission goes through
That's
a
the barrier.
process of deformation of the nuclei.
That requires energy.
Yeah.
Yes, that is the barrier. But the photon supplies that energy. Now there's no barrier left. And again, I wish to stress, this is not my theory. I wish it was.
La teoria che descrive questo, che non mi avete lasciato finire, è proprio che hanno fatto il 56 Teller, e non puoi dire che lui non sapeva la sua fisica teorica, ha usato il liquid drop model di Bohr per dire, per esempio, due big drop symmetric fission sono due uguali. Bene? Se qui stiamo parlando del fotone che ce l'ha fra 20 milioni di electron volt,
24 metri, sì.
ok? Non stiamo parlando di come centro di sole di 1.6 keV. È questo che sta dicendo. Uno ha bisogno di far andare a una cosa, okay? E così questa è una teoria che ha fatto Teller, eccetera, eccetera.
Sì, sì.
I believe at some point this theory won a Nobel Prize, not by me. I wish it was my theory. Okay, in addition to getting fit, it is the standard theory, but it is not mine. However, the only thing that we're doing is we're saying you can get this way by what Yogi calls a smart material, by crushing rocks in the right way. And you can get this by creating cracks, and you can also get it by creating cavitation. And one experimentalist we've known who has seen the nuclear transmutations and cavitation didn't take into account the effects of high-energy neutrons, and he had to be hospitalized for radiation, which is a very serious thing, and he never ran it full blast after that. So that these cavitation things, as well as that, will give rise to this new kind of low-energy nuclear reaction. I think I made that in 20 minutes. The final conclusions are, for this part, is that cracking rocks and cavitation can accelerate electrons to the point where they kick a nucleus into the compound nucleus of one of the Bohrs. I don't know which Bohr it was. It wasn't Niels Bohr. Son of Niels Bohr. And from that point, once you've kicked the nucleus hard enough, it can then fission. The compound nucleus decays all by itself with no barrier left. And I would like to thank the experimentalists at the Politecnico di Torino for educating. You know, usually if you go visit to give a talk, you're hoping you educate the people. When I went to Torino, they educated me. There's a whole field. There's a whole field, and us. It's a whole field of physics, which is going to work its way through. And you can tell that because as soon as they started reporting this, they were in a lot of trouble. And that's how you tell you're doing something really good.
Domande per Alan? Questione? Prego.
Adesso domande per tutti.
Vabbè, cominciamo da questo ultimo.
Just to understand, what you show is the usual photofragmentation of nuclei. It's
Absolutely.
It is an ordinary. But what is amazing is the process that you described first. That a proton plus an electron can produce a neutron. This happens, but in neutron stars. So you must have, that is the process that produces the neutron stars. So you must have such a huge amount of matter for doing that. Otherwise, the spontaneous process is the reverse. A neutron left alone, standing alone, decays into a proton plus an electron, not the reverse.
Right, unless you have an electron pulse which contains, let's say, 40 MeV electrons or 50. Then the electrons can kick it hard enough or create that. You're absolutely right. You're saying what I said, that photodisintegration of the nucleus.
It's an ordinary phenomenon.
Yeah, well, you're saying what?
Of course, if you have
I wish it was
photon.
my theory, but it was much, even an old guy like me, it was much before me. They understood this. However, I'll give you one thing when you're talking about needing neutron stars. If you look at the cosmology people whose predictions I worry about. But if you do look at it and you say, what are the abundances out there? There's lots of iron, almost no aluminum. When you look on Earth, if you're inland, there's more iron than aluminum. But if you're at the shorelines where there are a lot of earthquakes, there's more aluminum than iron. And you can't get that from a supernova. You cannot get that from a supernova because whatever the supernovas do, and I don't think people know so well what they do, but whatever it is they do is not getting you past iron, but on Earth you are past iron. And if you take an iron meteor, by the time it gets through the atmosphere and crashes, it's got a lot of aluminum in it. So, yes, these ideas, experimentally for me, are a month old. The theory is ancient, that's what I was trying to explain. The theory, even I say it's ancient, and I'm 72. But, you know, it's not my theory. This was understood long before, except the part that's sort of amazing, and I agree with you, is that you can get so much oomph from cracking a rock. And piezoelectric things can give you that kind of... That's our plan.
To summarize, everything is correct if you have enough energy.
Yes.
That usually is present only on stars. Supernovas.
Absolute agreement. Absolute agreement with you. That's right. We're absolute agreement with you.
That's why